jet of water spouting 140 meters into the air. This is Switzerland's second largest city, Geneva. In 2008, underneath this city and extending into neighboring France, a gigantic experimental facility, 27 kilometers in circumference, was built. That's 50 times the circumference of the Colosseum. It was operated by CERN, the European Organization for Nuclear Research, with the participation of some 20 countries, including also the United States and Japan. This is where experiments took place to define a black hole, by creating one. Pipes were laid 100 meters underground. Protons were accelerated through it at high speed.
When we get up to top energy, the protons are going at 99.9999991 times the speed of light. So very, very, very close to the speed of light. And then we're down the way. We're going to collide them inside the big experiments and see what we can see.
When protons traveling at such blinding speed collide, they are smashed into infinitesimal bits. And at the moment of impact, it was thought microscopic black holes would be produced.
Producing black holes is certainly a possibility. In many ways, a very exciting possibility.
However, lawsuits were filed in Germany and the United States, demanding an injunction against such an allegedly dangerous experiment. The lawsuits argued that no matter how small the black hole, once it started swallowing matter, it would become an unstoppable force. Eventually, so the claim went, our entire planet would be sucked in. The black hole. To trace its conceptual origins, we must go back 3.5 centuries to the time of Isaac Newton. Based on his law of universal gravitation, scientists of his era came up with a fascinating hypothesis. The more massive a celestial body is, the stronger its gravity. The lighter it is, the weaker its gravity. So its mass determines the speed necessary to escape from its gravitational pull. For example, the speed necessary to escape Earth's gravity is 11 kilometers per second. A more massive object would require a faster escape velocity. Light travels at a speed of 300,000 kilometers per second. So the more massive a star is, the harder it must be for its own light to escape. Theoretically, there could exist in the universe an object so massive that not even light could escape its gravitational pull. If we could not see this star shine, it would be, effectively, a black star. That was our first conception of what we now call a black hole. Black holes were studied more rigorously starting about a century ago. That was thanks to another of the great geniuses of physics, Albert Einstein. It was Einstein who predicted the curvature of space-time. This was his famous general theory of relativity. Gravitational forces distort the very fabric of the space-time continuum. The more gravitationally powerful a star is, the more it distorts space-time. so that light, instead of following a straight path, curves, a prediction confirmed by direct observation. German physicist Karl Schwarzschild was the first to provide exact solutions to certain equations in Einstein's theory, equations that describe the effects of gravity on space-time. Shrink a celestial object in size but not mass. Its density and the curvature of nearby space-time relative to size both increase. Continue shrinking it, and the space-time curvature increases to infinity. For example, if something the size of the Sun were shrunk to a radius of 3 kilometers, or the Earth to a radius of 9 millimeters, the curvature would be infinite. Light itself would be unable to escape, so the object would be invisible. That boundary is known as the event horizon. It is the origin of a black hole. So the thinking was, if subatomic particles were smashed into super-dense bits, that could also create a black hole. But then, no matter how small, wouldn't such a black hole grow monstrously, engulfing everything around it, eventually swallowing up the entire planet? That's why those lawsuits sought to stop the experiment in Geneva. Physicist John Ellis holds that the device in Geneva, the Large Hadron Collider, or LHC, poses no danger at all.
There's absolutely no worry at all about black holes that might be produced by the LHC. If the LHC can make any black holes at all, then cosmic rays, particles from outer space, that have been hitting the Earth for billions of years, have been producing these black holes, and we're still here. So they can't be dangerous.
Countless particles are constantly hurtling toward Earth at the speed of light and smashing to bits upon impact with our atmosphere, creating incredibly tiny black holes. But Ellis and other physicists argued that the lifespan of these tiny black holes is also incredibly brief. These arguments prevailed, and the injunction was denied. What strange properties. The power to swallow up anything and everything, but too short a lifespan to do that in. Black holes have an even more wondrous property. Professor Andrew Hamilton of the University of Colorado uses computers to create and evaluate remarkable phenomena involving black holes.
The wonderful thing about Einstein's general relativity is that it is an extremely precise theory. It's embodied in a set of equations which look, well, they're just an equation that relates curvature to the energy momentum content of space-time. And what does it mean? It's a bunch of mathematics. But the miracle of that is that you can ask the mathematics questions. What is the structure of the space-time, and how do things move in that space-time, and code that up as if you were writing a video game in software and see what it looks like.
This is one of Hamilton's computer-generated black holes. But the horizon of this so-called hole actually has the shape of a sphere. Map a grid of lines onto its surface, like those indicating Earth's latitude and longitude, and 2 points stand out. The black hole has a north pole and a south pole.
You can see the north pole and south pole of the grid simultaneously again. This is because the black hole is able to bend light around it so that you can see simultaneously the north and the south pole. Not something that you could see if you looked at the Earth, for example, from out in the solar system.
Look what happens if you simply toss a cubical box at a black hole. One would expect anything at all to be sucked in, yet the box sails on by. Why is that so?
This is a feature of black holes, is that they do not suck. Let's go back down to the black hole here. They don't suck. If you want to throw something into a black hole, you have to aim, and aim carefully.
So this time, a box is pitched directly at the center. The box twists under the stress of powerful gravitational forces. It falls towards the black hole. But strange phenomena continue to occur. One expects the box to disappear instantly into the black hole, but instead, it stays visible as it slowly falls. When it's finally reached the black hole, it seems to rest there, stuck on the surface. What's the explanation for that? As an object approaches a black hole, the gravitational attraction increases rapidly, and according to the theory of relativity, the stronger the gravity, the slower the passage of time. At the event horizon, time actually freezes. As the box falls towards the black hole, it accelerates rapidly. But from the outside, time appears to slow down the closer the box gets. So eventually, the speed of the box seems to let up gradually. Finally, when it reaches the event horizon, the box seems to stop moving.
As the probe approaches the horizon, it appears to slow down and freeze. Now, in reality, the image would not only slow down and freeze, but also become very dark. We would see very few photons emerging from this probe, so it would appear to fade to black. But for the sake of seeing what's happening here, I've kept it bright so that you can see the probe has become frozen on the horizon.
A black hole is truly a strange object in space. It may collapse as soon as it forms, yet it's powerful enough to stop time. So how was the existence of black holes verified?
Doctor, what are you doing? I'm making a black hole. So a black hole of this size would weigh roughly 10 times what the Earth weighs. So this would be a very, very heavy black hole.
Kip Thorne is a physicist whose search for black holes is based on Einstein's general theory of relativity. But he also pursues original topics, such as time-defying wormholes and time machines. His interest in the subject was first aroused by the intense scholarly debates over the very existence of black holes. The controversy raged for more than half a century. Thorne was in direct touch with the principal figures in those debates. He researched the entire controversy in detail for the benefit of future generations of scholars.
Well, there was great resistance to the idea of black holes. The opposition much of it was motivated by the view that this object is so bizarre, so strange, that it's unphysical, and it's not likely that the true laws of physics will predict such a thing.
This is Chennai, on the east coast of India. At a college in this city in 1929, a young scientist first argued for the actual existence of black holes in our universe. Subramanian Chandrasekhar. His work at the age of 19 on the internal structures of stars won him admission to the University of Cambridge for postgraduate studies. On board the ship to England, Chandrasekhar gave some thought to white dwarf stars nearing the end of their life cycle. One could say that modern black hole studies began with ancient white dwarfs. A star normally burns furiously, balancing gravitational forces that could collapse it and explosive forces that could blow it up. But as its nuclear fuel is used up, the star cools, and with those expansionary pressures relenting, it begins to contract. Conventional theory held that a star contracts to about twice the size of the Earth, then it stops. That is what is called a white dwarf star. The reason why the contraction stops lies in the star's very atoms. As the star shrinks, its atoms are compressed. Conventional theory held that there are limits to that compression, beyond which further shrinkage is impossible. This is a white dwarf star, surrounded by an expanding nebula. The star, maximally compressed, is clearly recognizable within a cloud of gas and dust. A white dwarf star is compact and very heavy. In size, it may be comparable to Earth, but its mass is more like the Sun's, as if a lump of sugar weighed several tons. At the time of Chandrasekhar's passage to England, it was thought that all stars ended their lives as white dwarfs. Chandrasekhar based his arguments on his calculations of the changes undergone by white dwarfs as their density increased. His results were astounding. Beyond a certain mass, the white dwarfs shrank to infinity. Previous calculations held that the limit of a star's shrinkage would be a radius of 10,000 kilometers. But Chandrasekhar reckoned that if a star were at least 1.4 times the mass of our Sun, it would be unable to resist its own gravitational pressures. It would completely collapse, and shrinkage would continue infinitely. This is precisely what we now call a black hole. The black hole had emerged accidentally from a consideration of white dwarfs. Soon after arriving in Cambridge, Chandrasekhar presented a paper on his findings. Cambridge was then the academic home of Sir Arthur Eddington, one of the world's foremost experts on the internal structure of stars. Eddington was also famous as an explicator and defender of Albert Einstein's just-published general theory of relativity. All stars ended up as white dwarfs, thought Eddington. Surprisingly, he nonetheless praised Chandrasekhar's paper and promised to support it. But then,
the time came when Chandra was to present the results that he had to a meeting of, I think it was may have been either the Royal Astronomical Society or the Royal Society of London. I don't recall which. And right after he presented the results, Eddington got up and criticized them very severely.
Eddington's rebuttal was caustic indeed. The eminent scientist asserted that a star might collapse to a few kilometers radius, but no smaller. "I think there should be a law of nature," he said, "to prevent a star from behaving in this absurd way." Why exactly did Eddington criticize Chandrasekhar so harshly? Thorne believes that Eddington was simply being fierce in his pursuit of scientific truth.
It's my suspicion, I think it is likely, that in fact Eddington was treating Chandra at that time as a colleague. And in England at the time, there were serious intellectual battles between colleagues. But Chandra had not yet grown up to the point that he felt like he was a colleague of Eddington's. He felt it was an unequal match. But Eddington, I think, I suspect that Eddington admired Chandra. He always said he did.
After that, Chandrasekhar changed his workplace from England to the United States. Later, Thorne invited him to come to Caltech, and they developed a close relationship lasting until Chandrasekhar's death in 1995. In 1932, the black hole controversy again ignited. The spark was provided by a new theory in physics. It was known that an atomic nucleus was comprised of protons and neutrons. But under extreme compression, protons and electrons could combine, forming neutrons, and these could be compressed even further. That meant that the remaining mass of an exploded star 1.4 times larger than our Sun or greater could turn into a neutron star. Neutron stars can now actually be observed. The Crab Nebula is the remnant of a supernova explosion. A special camera can peer into its depths. The bright celestial body at the center of that gaseous disk is a neutron star. It is small but incredibly heavy, as if a lump of sugar weighed hundreds of millions of tons. Scientists at the time thought that dead stars must be either white dwarf stars or neutron stars. They denied the existence of black holes. At this point, however, a dissenting voice was raised, that of J. Robert Oppenheimer. A brilliant mathematician himself, Oppenheimer, like Chandrasekhar, calculated the mass of a neutron star. He found that a star at least triple the mass of our Sun would not stop at the neutron star stage, but would suffer complete gravitational collapse, contracting infinitely. This constituted the reappearance of the theory that black holes actually can exist in our universe. But a counterargument was put forward by John Wheeler, one of Oppenheimer's colleagues at Princeton University. When Kip Thorne was in graduate school, Wheeler was his mentor. As to why a massive star could not become a black hole, Wheeler argued as follows. He said that a dying star would discharge gases in a process that actually made it lighter, so every star would merely become a neutron star. We can actually observe an aging giant star emitting huge volumes of gas. The controversy between the two experts continued for over a decade. Wheeler was fierce in his refutations of Oppenheimer's thesis, but as he rechecked his calculations, he came to have doubts about his own position.
So, John Wheeler, like Albert Einstein, had very deep physical intuition and insights. And like Einstein, he was usually right, sometimes wrong.
Finally, even Wheeler accepted the existence of black holes. He then pushed forward the study of black holes even further than Oppenheimer. In fact, it was actually Wheeler who gave these strange, infinitely contracting celestial bodies the name of black holes. With Wheeler's conversion, a half-century of controversy among scientists was concluded. It was now accepted as indisputable that dying giant stars, unable to withstand their own gravitational forces, would contract infinitely, forming black holes. was Subramanian Chandrasekhar who set scientists on the path that led them to acknowledge the existence of black holes in our universe. In 1983, Chandrasekhar's work on the structure of stars and their evolution was recognized when he was named as co-recipient of the Nobel Prize for Physics.
And I sent him a note of congratulations, and he acknowledged it. But I think we never discussed the Nobel Prize. But he was, among scientists I've known, he was one of the most self-critical and the most intensely driven, but driven from within and not driven to receive acknowledgement from other people for his discoveries.
The result: not only were black holes acknowledged as existing, but light was shed even on the processes by which they were born. And yet, they existed only in theory. Actually discovering a black hole was a dream of many a scientist, among them a young Japanese enthusiast. Boston, Massachusetts, USA. A certain Japanese man regularly stopped by this pet shop in 1963. He seemed to like watching mice and other small animals there. Little did anyone suspect that their activities concealed a key to the development of black holes. Minoru Oda was at that time a visiting faculty member at the Massachusetts Institute of Technology. An MIT research group had launched cutting-edge imaging equipment by rocket to obtain X-ray images from outer space. Bruno Rossi was in charge of these observations. He was also the one who had invited Oda to the United States. It was known that the sun emitted X-rays. However, X radiation from other celestial bodies is absorbed by the Earth's atmosphere. Hardly any of it could be detected by Earth-based observation. Rossi's group, working on the hypothesis that there must be other X-ray emitting celestial bodies, used a rocket to detect this radiation. They found even stronger X-rays than they had expected. The equipment they used, however, could not tell them much about the direction the X-rays came from. Oda and Rossi talked it over at the beach one summer. The area marked in red, they knew, emits X-rays. And they knew it was in the constellation Cygnus. But they did not know whether the radiation emanated from particular stars, or more generally from that sector. So how could one pinpoint the source of those X-rays? Oda got a clue from the pet shop he'd been going to. Oda was fascinated by seeing something alternately hidden and revealed. When he got back to Japan, he applied his insight to the development of an imaging device. Here are Oda's prototypes. Looking at the arrays of fine wires, he called his invention a screen collimator. When two or more of these screens were placed in front of a detector, even slight differences in the origin of X-rays would cause some to pass through, some to be blocked. The concept was that that could help refine estimates of directionality. At the time, however, Japan had no rocket with which to launch such a device. So Oda, determined to pinpoint the source of that X radiation, devised another way to provide his device with a space-based platform. There is archival video of his effort. The experiment took place in Fukushima, Japan in 1966. Oda sent his screen collimator aloft in a balloon.
気球はいろいろな観測機を積んで高度 30km の成層圏まで上昇します。高度 30km あたりでは気圧も地上のおよそ100分の1になり、宇宙の彼方から飛んでくる X 線、ガンマ線などの放射線や赤外線、陽子、電子などを空気に邪魔されることなく、ほとんどそのままの姿で観測することができます。
When its observations were done, it descended by parachute for recovery at sea or in the mountains. Observational missions using Oda's collimator continued for 4 years. This helped narrow down the source of the X-rays. The yellow oval marks the area identified by the collimator as containing the source. It was a limited area. In 1970, the U.S. launched Uhuru, the world's first satellite for the detection of X-rays. Its very first observations were of those mysterious X-rays. Oda was a guest investigator for this project. Uhuru refined further the calculations regarding the source of the X-rays. Even more detailed observations followed. April 1971. At last, the origin of the X-rays was pinpointed. It had taken 7 years to solve the riddle. Near the source of the X-rays was a blue supergiant star some 30 times the mass of our Sun. Analysis of the light from that star produced a startling discovery. The color of the star was changing slightly. That indicated movement. Further analysis showed that the star was circling some other object in a brief cycle lasting 5.6 days for one revolution. It would take a massive object indeed to keep a supergiant star in its orbit. From the blue supergiant star's movement and spectra, the mass of its unseen partner was estimated as being equivalent to 10 of our suns. But that celestial body could not be found at the expected location. A star 10 times the mass of the Sun, and yet invisible to us, emitting powerful X-rays as well. It had to be a black hole, the first actual black hole ever discovered through observation. It was named Cygnus X1. Kip Thorne was one of many scientists delighted by this discovery.
Oh, it was very exciting when Cygnus X1 was observed. There had been predictions by several astrophysicists that if you had a black hole and it captured matter from star, it would produce X-rays.
When Cygnus X1 was found to be the source of those intense X-ray emissions, Thorne made a bet with his friend, theoretical physicist Stephen Hawking, as to whether it was a black hole or not. This is the wager, as written. Thorne bet that Cygnus X1 was a black hole. Hawking bet against that proposition. At stake were magazine subscriptions. After the initial discovery of Cygnus X1, it was observed further. Examination of data on its mass and on variations in its X-ray emissions led to a broad scientific consensus that this was indeed a black hole. In 1990, 16 years after the wager was made, Hawking's concession was duly noted on the original betting contract.
He bet that Cygnus X1 was not a black hole, and he hoped that he was wrong. And I bet that it was a black hole.
No one was more cautious than Hawking in interpreting observational data, and now even he acknowledged Cygnus X1 to be a black hole. After the initial discovery of Cygnus X1, Japan launched a series of satellites for X-ray observation, making significant contributions to the study of black holes. ASCA, launched in 1993, undertook further observations of Cygnus X1, obtaining a wealth of detailed data. The first black hole ever discovered. Its location, around the middle of the neck of the constellation Cygnus, the Swan, 7,500 light-years from Earth. The black hole and its companion star are paired in what is called a binary system. They are only 30 million kilometers apart. That's less than the distance between the Sun and Mercury. Gases from the blue supergiant stream to the black hole. The gases, heated by friction, reach temperatures as high as 10 million degrees Celsius and generate powerful X-rays. The mass of the black hole is equal to more than 13 of our suns, yet its radius is a mere 40 kilometers. Above and below the black hole are two jets. The discovery and elucidation of this system has ended 50 years of scientific controversy. Minoru Oda contributed to the first ever discovery of a black hole. His concepts and inventiveness turned the impossible into the possible. That legacy continues to inspire. Can one see a black hole with the naked eye? Scientists on the cosmic front are now trying to undertake direct observations of black holes. But can that be done? With formulas derived from the general theory of relativity, Rota Takahashi tried to deduce mathematically what a black hole would look like when directly observed. It took him 4 years to arrive at a solution.
宇宙の中で一番時空が歪んだっていう、もう本当に特別の特別なところなので、そこをやはり見てみたい。しかもこの写真とか動画として見てみたいっていう思いがあります。
This is how Cygnus X1 is currently imagined, based on observed data. The black hole is deep in the bottom of that dark center area. If one could see it with a sufficiently powerful telescope, this is what it would look like. The gases that have been sucked into the black hole are superheated by that violent friction and shine brightly. That bright light makes the invisible black hole appear to take the form of a black ball. This phenomenon is called a black hole shadow. The bright light to the left of the ball is from the superheated gases, which are forming a disk spinning at high speed. Even some background light is visible at the fringes, despite the gravity-induced invisibility of the black hole itself. Unfortunately, says Takahashi, Cygnus X1 is too small a black hole to be observed more directly with today's technology. A black hole that is easier to view has been found, however, right in the middle of our own Milky Way galaxy. Equivalent in mass to 4 million of our suns, this is a monster black hole. Its event horizon radius exceeds 10 million kilometers, so large that it would look quite different from a small black hole like Cygnus X1. Assuming it could be observed from Earth, Takahashi envisions it as looking like this.
現実のブラックホールっていうのはガスを吸い込んではいるんですけど、ある時には多くガスを吸い込んで、ある時には少なく吸い込んでる。ガスを吸い込む量っていうのが時間変動します。明るく例えばいきなりパッて光る時、例えば今みたいに光った時っていうのはガスをたくさん吸い込んでる時です。で一方でこういうふうに暗くなった場合、ガスをあまり吸い込んでない時です。だからこの明るさの光り方を見ると、ブラックホールがどの程度ガスをその瞬間に吸い込んでるのかっていうのが分かるような感じになっています。
Takahashi has calculated just how strong a telescope would be needed to observe this black hole from Earth. It would have to be powerful enough so that from Tokyo, one could make out the baby hairs on the face of someone standing on the summit of Mount Fuji, 100 kilometers away. The attempt has already begun. MIT's Haystack Observatory in the suburbs of Boston. Shepard Dolman has been cooperating with the National Astronomical Observatory of Japan in the effort to observe a black hole directly. Here, data from radio telescopes all over the world are combined and analyzed. They may not have a telescope capable of seeing from Tokyo the baby hairs on someone standing on Mount Fuji, but they can emulate that power.
And to get the high angular resolution that you need to see the event horizon, the boundary of the black hole, we create an Earth-sized virtual telescope using radio telescopes spread all around Earth. And we tie them together to make a picture as though we had a telescope as large as the Earth itself.
At the U.S. National Radio Astronomy Observatory, they have an array of 27 parabolic antennas, each 25 meters in diameter. The diameter of the remote telescopes is determined by the desired resolution of the image. By combining data from multiple remote telescopes, one can emulate the capabilities of one giant telescope and obtain high-resolution images. To obtain the highest possible resolution in their effort to capture a black hole shadow, Dolman and his colleagues used sub-millimeter telescopes. This technology is called Very Long Baseline Interferometry. The plan calls for linking 3 sub-millimeter telescopes in Hawaii, California, and Chile to emulate one gigantic Earth-sized telescope.
We really hope that in 5 years, we have started to make very good progress on actually making an image of the black hole itself.
In the near future, we will be able to peer directly into a black hole. The invisible black hole. At first it was a theoretical proposition, but its reality has been confirmed, and a consensus has emerged. Actual observations have produced scientific proof that black holes exist in our universe.